Tombstone bumper cars. Oh. Oh. I have to do better.
Struggling how to end that commercial, balls of steel.
We already did the brick, and then you did the hammer.
Cut to black!
Yeah, cut to black. That's an excellent idea.
Yeah.
So I came up with this random way to talk about this rather interesting comment that I got right here. And I'm not going to put the person's name. They also gave me some really helpful advice with the machining, which is so much appreciated. Thank you so much. I just want to, sort of open the discussion a little bit, whether you use guns or you don't use guns, or you like guns or you hate guns. It's just really not a matter of fact. Newton's fourth law of motion is not that guns are the best way to protect yourself. Maybe just think about what the future could look like. But then we also have to think about the different kinds of defense. What kind of situations will people be in where they need to defend themselves? If it's home defense, firearms may be the best way to do that. There are a lot of people who carry things like mace or pepper spray, intentionally non-lethal methods of self-defense. And like this person said, the device does not really need to exhibit a capacity for murder to be able to be an effective deterrent. When they're having a night out, or they live in a bad neighborhood and have to walk home. Ladies, you know what I'm talking about. Men, talk to your girlfriends. You're having a night out. You could encounter people who are dangerous and they might not be armed. And mace and pepper spray is a very effective deterrent for these people. A lot of the crimes that are executed against women where mace or pepper spray might come in handy, these crimes are more likely to be executed by people they know as opposed to complete strangers. I think this is a valid criticism, and I'm not going to tell you that this thing that I painstakingly manufactured with my crappy machine is going to change the world. What we're trying to create here is something that is sleek. I know it's not yet, but it will be. Something that's easy to use. I know it's not yet, but it will be. And something that's stylish. And I know it's not yet, but it will be. Something that can be used by both men and women to just sort of enhance their own abilities in the face of people who might do them harm. Let's just make sure we keep our minds open and continue with this project to try to make it the best and most effective version of itself. It's been 9 days since I filled this thing up for the first time, sealed it up, and I thought there might be some small leaks inside, and it's possible there are some really small ones. Still got a good amount of liquid in it. So now we have to talk about what is next with this thing. This obviously is not good on its own. This valve, you have to pull it down like this. There's nothing even to fasten it to your wrist. Welcome back to another video, everyone. This one is just going to be some quick light fun, and there might be a mathematical lecture or two. While I try to fit this bracelet, currently just a pressure vessel, with some other stuff, it needs to function as a wrist-mounted material ejection device. I'm still workshopping a name that won't get me sued. This video is sponsored by Dragline Dynamics. Are you a... Hey. Huh? Hey, sorry, it's just, you've said this for every video for the last few videos, and I'm confused. Okay. It's just, this is your company, and this is your video, so how exactly is this a sponsorship? Well, I'm paying myself for advertisement, hence self-sponsorship. Okay, I guess that makes sense. Are you a superhero in need of a new look? Check this out. It's called Symbol Light. It's a super flexible, concealable LED light, which you can buy customized with your symbol today. Just visit dragline.tech. If you want to make your dream superpowers a reality, or you just need some tutoring in a tough subject like math, physics, or engineering, schedule a 30-minute session with me and take advantage of 10 years worth of knowledge for just $10. Visit dragline.tech. Dragline Dynamics aims to democratize technology for modern heroes, and that means you. You should probably get a different sponsor next time so you can make some real money. So the first thing I want to work on in this video is having something where this device becomes super easy to just snap onto your wrist. You can see in a lot of my older videos, I have buckles and straps and Velcro and like all this stuff, and you can see me struggle. I cut it out a lot of the times, but you can see me struggle. So to start out with an efficient fastening method, I've created this little mock-up here. It's about the same size as this thing, but you'll see that it's a full bracelet. This is built in 3 parts. You've got the partial bracelet here, and then you've got these 2 parts that are on a pivot point. So when you want to put this on, I want you to imagine you're just, full bracelet. You're just going at it just like this. And then let's say there are some springs that bring these back around. Then when you want to take it off, there's some button that undoes this latch, and then you simply pull it off just like that. So there's another version of this that I'm about to try out. Since this is just a mock-up, I didn't want to print another one to waste the plastic. So this would be like this, and then this would have to, ooh, yeah, I don't like that. Ouch! This point here is digging into me. This is gonna be way better with 2 pieces instead of 1. That's great. I like that a lot. So what I'm going to do is I'm going to see if I can design this a little bit further such that we have the spring mechanism and the latching mechanism, and hopefully it will become more clear what the idea is here. So I've made a lot of progress with trying to figure out the spring mechanism in the clasp, as well as any locking mechanisms that need to happen, such that we can get the perfect behavior we want from this thing. So originally, of course, I try to use mechanical springs, and I don't want these to take up a lot of space. We have this huge pressure vessel to account for. So I started using these really tiny, like 2 millimeter wide tension springs, and these are really difficult to work with, and the assembly gets really frustrating. It's a tension spring, it works. It returns to the position it's supposed to be in, but the assembly is difficult. So I started continuing with the tension spring idea and even thought about having a latch. So I designed this, but as you can see, it doesn't stop it from moving up. It stops it from moving down. And as I was assembling this, you can see I messed up one of these tiny springs. So this was kind of the moment where I was like, okay, these tiny springs are really just not worth it. There has to be something better. And I realized that I could use magnets. This is a suggestion from my girlfriend, actually, who's also an engineer. So these are 10 millimeter diameter neodymium magnets, and they're very strong. They kind of work as a spring, a super flat spring, because they can slide against each other. Ooh. Such that the magnets are always close to each other. We don't have to deal with the fact that magnetic forces are very weak as distances become large. You have your axis of rotation here. Obviously, your axis is not a point. It has some dimension, about 3 millimeters here. So one magnet would be here, and that's on one part. And I only need this to rotate 90 degrees. So on the other part, I place the magnet 90 degrees away, like this. So even when this part is fully rotated at 90 degrees, the magnets still have this overlap that allows them to still, interact somewhat strongly, even though what they want to do is bring this center to that center. I also realized, because I'm an avid watcher of many 3D print designers on Instagram, that I could actually easily embed these magnets inside the 3D print by placing them into the 3D print in the middle of printing. And that's a technique that I did not come up with, but it is super handy. So there's just a magnet inside there and a magnet inside there, and you can see they stick together. And there's no fasteners needed, no glue needed. This is the magnetic spring. I also added sort of a stop. This can only rotate 90 degrees. And I also added a little latch mechanism. So you can see here, there's a little leaf spring here. This leaf spring looks like this on the inside. And it's super easy assembly. All I have to do is stick this thing into this hole here. And this leaf spring prevents this from rotating. And my successful wristband is this one. Hold these leaf springs like this, which is still kind of difficult. I might want to think about a better way to do that. But you basically pull the leaf springs, clip this here, and it goes on just like that. And there it is. And then to take it off, pull those leaf springs again, break it, and just like that. I do think I want to add more magnets like here so that this can nicely kind of adhere together. So we're getting there. It's not perfect yet, but definitely very close. So we've sort of figured out the clasp mechanism. It needs some adjustment to make it perfect, but I think this is a pretty nice idea. overall. The only issue is this kind of leaves minimal room for everything else in the wristband. The part of this clasp mock-up that doesn't move is actually mostly taken up by the pressure vessel itself. But the thing is, this is definitely the clasp mechanism that I want to go with. So we're gonna have to have some creative solutions to figure out where to put everything else that goes into this device. To start, I want to focus on the valve actuation. There's a bunch of different mechanisms that I've created for valve actuation in the past. Levers, screws, gears, pulleys, capstans, all sorts of things. I really want to try to streamline it, come up with something that's compact or at least fits, sort of within this C shape, and something that is optimized from an engineering standpoint in the sense of, what is the minimal transmission that we need such that our actuator can open this valve. It takes quite a lot of force to open this valve. I don't know exactly how much, but the first step in figuring out what kind of transmission we need is to actually measure that amount of force. All right, so I've mounted my pressure vessel to the table here. The liquid will be at the bottom of this pressure vessel because of gravity, and that means that I can see when a stream is coming out, because if it was vapor, it would be invisible. And then I have this sort of like a marionette controller. I have no idea what that's called. I've built it such that it's just a single rope winding through this entire thing so that the tension is the same, and this mounts right here. And I've got this thing attached to this spring force gauge, and I can pull on that. Sorry, it's not very sophisticated. I intend to just take like slow motion video from directly below and sort of just watch what the reading on the force gauge is at the instant the valve is opened. I've been doing a great job so far with my bi-weekly Friday 5 p.m. schedule, which is tricky since I'm actively working on my PhD. Be sure to check out my 8-legged robot Charlotte, or my repelling invention, or my Instagram at the.amazing.labs. If you want to help me continue innovating within all of these avenues, support me with just $1 per month at patreon.com/theamazing. Or I accept one-time donations via PayPal at the email draglinedynamics@gmail.com. And remember, all you have to do to support the channel is subscribe. Now, back to the video. Now, while I originally planned to view this video and try to discern the force from it manually, I actually realized I could use some computer vision techniques. So I ended up isolating the stream of fluid, doing some segmentation, then doing some thresholding. And that actually gave me a pretty accurate numerical value for whether or not the valve is open. Then I could do some motion tracking on the force gauge, and registering that to real-world measurements, I was able to get a value for the force from the video. And so I could overlap these two graphs and then only sample the force readings above a certain valve opening threshold. That gave me an average force of opening the valve of about 20 newtons and a maximum force of about 28 newtons. This contrasts with another analysis I did, that is the force based on the vapor pressure and the diameter of the outlet, and that only predicted about 5.6 newtons. So there must be quite a lot of friction, or there must be some other force acting upon this valve when it tries to open. Of course, measuring the force that it takes to open the valve is only one side of the equation. To design a transmission, we need to also know how much torque this motor can exert. And I don't really have a number on that, so I decided to just measure it. So I'm going to put this all together and collect force values at various voltages for this motor. Here I've plotted these torque measurements as a function of the voltage they were measured at, and it seems like it's a pretty linear relationship. That means we can fit a good old y equals mx plus b to these points. Since we got this data of how much force it takes to open the valve and how much force the motor can exert, we need to talk about how we can use that information to design this transmission. So the thing is, transmissions are all about an equivalency of power. So power in has to equal power out. Now that's assuming efficiency is 100%, and this essentially would only not be true if there's friction in this transmission, which of course there will be, but certain types of transmissions are closer to 100% efficiency than others. What is power in? It's equal to the torque multiplied by the speed. Now this speed is in radians per second, but we can turn it into rotations per second by multiplying it by 2 pi. Here we represent rotational speed as n rotations divided by t time. On the valve side, we have this valve that has to move a certain distance, x. And the force that's exerted as it moves this distance is F. That's what we measured. Now we're going to assume this force is constant as the valve moves, and that means the work that is done, which I'll represent as W, is equal to F times X. So if we want to get the power that's transmitted to the valve, we simply have to divide work by time. Now the key equivalency between these two is that the amount of time it takes the motor to spin to open the valve is the same amount of time it takes the valve to open. First, let's start by setting power in equal to power out. Torque N 2 pi over T equals Fx over T. Since these times are the same, we have Fx equals T N 2 pi. Now we have this torque as a function of voltage. That's the data that we gathered for the motor. And if we rearrange this, we can have the number of rotations that are required to open the valve as a function of voltage as well. Now this is actually a lower bound. Essentially what this is telling you is that it's not physically possible to open this valve with any number of rotations less than this amount. So this becomes our lower bound for what is possible. But then there's a question of what is this torque exactly? A key characteristic graph of a motor looks something like this. So if this is torque and this is speed, this is called the stall torque, and that's what we measured. It's the torque when speed is 0. This is called the no-load speed, and that is because it's the speed when the torque is 0. Now, what about the effect of different voltages? Because we measured this stall torque at several voltages. Let's say this is the graph when voltage equals 1. What happens if we increase the voltage to, let's say, 2, is just it shifts the curve upward like this. So you can see we do have that increase in stall torque that we observed from our graph. And our data for stall torque, depending on voltage, had a very linear relationship with an intercept at 0. And we fit a best line to it. And this relationship actually is theoretically expected. And the reason for that is because you can model any DC motor as a voltage applied across an armature that has some inductance and some resistance, and being applied across another voltage where the voltage across this is equal to the motor constant K times the speed, and this is called back EMF. Now, when we're at stall torque, the speed is 0. This inductor, which usually has the equation voltage across the inductor is equal to the change in current, but because we're at steady state, current isn't changing. The voltage across this goes to 0. We're just left with a simple voltage V across a resistor R, and that exhibits the current I equals V over R. That's Ohm's law. So that's a linear relationship between voltage and current. And I want to be clear here that this current is the stall current, IS. And because torque is always proportional to current with this same constant K, the stall torque is proportional to voltage over resistance. The slope of this line is K over R. Hi, it's me editing here, and I just wanted to say I did measure the resistance of the motor, and it's about 7.5 ohms, which means we can actually calculate the motor constant without ever measuring current, and we get a motor constant of about 0.05. So it's kind of cool we got all that just by, taking a few measurements, but we don't want to run this transmission at the stall torque, right? Stall torque means the motor isn't moving. So we do need it to move. Now recall that the power that a motor transmits, as we talked about just briefly before, is equal to the torque multiplied by the speed. When you define your operating point on this curve, power is actually the area of the rectangle that's formed between the origin and that operating point. So we actually get the maximum power transmission at the stall torque divided by 2. Now we can change sort of the ratio S. So right now we're talking about S equals 0.5. If you move S closer to 0.3, you have a little bit better efficiency, but we're going to be working on maximum power transmission. Now recall that this is an upper bound, meaning that any point in the upper green area will actually still function. It's just that anything below the green area is physically impossible. Now, when I first saw this curve, I thought, wow, these rotations actually look quite low. If we're operating at like 2.4 volts, we only have to do half a rotation? That seems crazy, and that's not been my experience in the past. But you have to remember that this is just what's physically possible according to physics. We can also examine this based on engineering. So if we have to pull the valve backwards a distance of x, we can imagine using a string attached to a winch. Now this winch has a diameter, which I'll call d in. We need to rotate this only 0.5. So that means that x, the amount that this is pulled, is equal to the circumference d in times pi multiplied by the number of times it's rotated. D in is equal to x divided by pi n. Now, if we plug in some numbers here, x is actually quite small, 0.00088 meters. This is defined by the design of the valve. It's going to be something like 0.0006 meters.
You're not impressing my stream. Everyone knows you're using a calc. Calc is calculator for short, chat. So what? Okay.
0.6 millimeters. Yeah, so that's not happening. And also, I don't want to do cable-driven mechanisms anyway, because they're really difficult to assemble. And the motor shaft is actually 3 millimeters in diameter. So we really can't get away with any D in less than 3 millimeters, and probably should be even more than 3 millimeters. So how do we solve this problem, this constraint on the input diameter? This is where a transmission would come in. We can rewrite our equation for D, again, as a function of voltage. This time we plug in our function for N as a function of voltage in the denominator. If we add a transmission, this equation for N is not going to change. So that means that everything in the denominator here remains the same. So if we want to increase the diameter of the input, we have to increase the input stroke. What we can do is add a transmission such that the input stroke X is actually equal to some gear ratio. We're not going to use gears, multiplied by the distance that the valve has to pull. Similarly, the force that goes into this transmission is equal to the force the valve needs to open divided by that ratio G. How many turns do we want the motor to have to do to open the valve? So if we have number of turns greater than 1, now we're talking about we have to do things like gears or belts, like transmissions that can go greater than 360 degrees. If we keep N less than 1, suddenly we're thinking about using things like cams, slots. And there's a specific type of mechanism that I have my eye on, and that is where N is equal to 0.5, or a half turn. So I want you to imagine that your motor is driving a wheel, and this wheel is attached to some peg, and this peg is transmitting force to a lever, which has a pivot point here. And so as we get that half turn, the motor moves the peg this way. It ends up here at its farthest point, at its farthest point horizontally, and finally ends up here. This means, of course, that this peg needs to have a slot to accommodate that horizontal movement. As the motor moves through its half turn, this lever will end up rotating about this pivot point to a final position here. We can also change the pivot point on this lever to get different kinds of mechanical advantage. So let's say this lever gives us a mechanical advantage of L1. We have our valve moving back and forth. The question is, what kind of L1 is necessary to modulate this distance such that D in will rise above 3 millimeters for a reasonably low voltage? The amount of space we have to work with is just what's on this bracelet. Here we have our motor, and the motor has an axis here. So I want you to imagine this wheel that we drew here is right here, being driven by that motor. So when you look at it from the front, you'll see the circular shape, but on this side you just see that. And the valve that we have to actuate is down here. That motion is along this axis. So what we could do is we could have that lever essentially with a pivot point here, basically rotating like this, and that lever basically takes up this whole space. A mechanical advantage is the ratio between this distance and this tiny distance here. So we can see by modulating our D of V model, by adding G and modulating X, suddenly we see at 2.4 volts, this transmission becomes possible from an engineering standpoint because D is suddenly above 3 millimeters. What I actually decided to do, this part is taken up by some lever that has a mechanical advantage, and this part is taken up by another lever. Our G actually becomes L1 times L2. When we add this G to modulate our D of V model, suddenly this becomes very feasible from an engineering standpoint. After tweaking the model a little bit, I got exact numbers that would work for L1 and L2, such that it would fit on this wristband and be able to actuate the valve theoretically at a very low voltage, possibly less than 3 volts. I don't expect it to be that low in real life. A very exciting prospect for me. Here we have the final product for this video. We've incorporated the clasp mechanism that I came up with. Do it like this. Look at that. Wow. And the valve actuation mechanism that I came up with by using math. This wheel here, this wheel, this lever, this one has a pivot point here, and then the second lever, this lever here, and has a pivot point there, actuates the valve. 2 levers taking up part of this wristband circumference, and the motor drives it with a single half turn. Now remember, in theory, we got this to work 2.5 volts. So we're gonna see if that is the truth. We're just gonna keep increasing the voltage until we find the lowest voltage that is capable of opening. Right. I don't think I've put that much propellant in it, but as soon as the valve opens, I'm just gonna point it out the window. So here's 2.5 volts. No, we hit the stall. Okay, 3 volts. That did it. 3 volts. 3 volts to control 90 psi of pressure. Solenoid valves eat your heart out. Wow, that's incredible. So the model was pretty close, actually. You have to reverse the polarity to reset, and next week we'll be adding a control system to do that. Well, I hope you guys enjoyed that. I definitely had a lot of fun with this project during this period of time. Super easy to put on here, super easy to take off. And I'm really happy I did the modeling with the motor. I don't think I would have had a design work on the first try if I hadn't done that. So next week we're gonna work on the controls, the electronics. That's really exciting. So tune in 2 weeks for that video. This is looking really good. For now, I'm gonna head inside because my fingers are freezing. I don't know why I decided to do this when there's a wind chill advisory going on. Yeah, so I'll see you guys in 2 weeks. Stay amazing.